Hello, today I want to show you how you can use RCC11 spreadsheet, a structural design spreadsheet to design structural elements such as slabs, beams, and columns. So I will be treating an example of a simply supported slab panel that is supported by beams and columns. We'll be designing this slab panel and the beam AB and the column B. Now, the initial element sizes that have been chosen for this example, all beams have sectional sizes of 225 mm by 450 mm. All columns have sectional sizes of 225 mm by 225 mm. And the slab thickness is 180 mm. Mm stands for millimeter. So the weights, concrete, 24 kilonewton per meter cubic, block wall, 2.47 kilonewton per meter squared, FCU, strength of concrete, is 25 newtons per millimeter squared. Fy, strength of steel, is 410 newton per millimeter squared. Live load for the slab panel is 1.5 kilonewton per meter squared and finishes of 1 kilonewton per meter squared. Okay, now before we proceed further, let's look at the RCC1 spreadsheet software. Now, this is the spreadsheet program, and we can see that it can be used for slab design. When you click on it on the slab design tab at the bottom here, we can do slab design, and the input parameters for it, we have design moment and other parameters such as sizes and dimensions. So it can also design simply supported. It can also be designed as a simply supported continuous span support or cantilever. So what we will need, the main parameter we will need to carry out the design using this spreadsheet is the design moment M, which we are going to calculate. Similarly, for the beam too, is the design moment M. And for column design, we have to calculate the axial loading. So we are going to start with the slab panel by estimating or calculating the design moment. Now, how to calculate design moment for slab panel A. So here is how I did it. Dead load is equal to weight of concrete times slab thickness. So, and which is equal to 24 kilonewton per meter cubic times 0.18 meters, which gives 4.32 kilonewton meters. That's the dead weight of the slab. Now, the total dead load, we add 4.32 kilonewton per meter squared plus finishes to give us 5.32 kilonewton per meter squared. Now, design load, according to BS code, is 1.4 GK plus 1.62 K, where GK and QK are dead and live load respectively. So, and we know that live load for private dwelling is 1.5 kilonewton per meter square. So, therefore, design load using this formula gives us 9.85 kilonewton per meter squared. And from the BS code, also we know that design moment for a slip supported slab is WL squared over 8, where W is equal to design load and L is equal to span. So WL squared over 8 will now be, in this case, to be 9.85 kilonewton per meter squared times 3.225 meters all over 8. Remember that the span of this slab is 3.225. This is the span of the slab, not this one, but this one. So, and the slab is a one-way slab. So, using that formula, we get 12.81 kilonewton meter. So now going back to our RCC11 spreadsheet program, we just have to change and input the parameter, the design moment, which is 12.81. So quickly, 12.81. And then the span is 3225. And then the thickness of the slab is 180. And then we can start with it. We can leave it at the bar of 12. This cover to 120. FCU 25 and FY is 410. So we quickly see that the program have designed it to give provide R12 as 250 center to center. Let's move on to the beam design. Now, as with the slab design, the main parameter we need to find is the design moment of the beam. So, beam design using RCC11. Now, this is the same slab panel. We want to design beam AB. So, and by studying this panel, we can see it's a one-way panel. To design beams using RCC11, you must first calculate the design moment. Design moment of beam AB. Since panel A is a one-way slab, beam AB will carry exactly half of panel A loading in addition to its own weight plus wall load. So to carry the exactly half of this slab panel be carried by beam AB, and in addition to the wall load on beam AB and the dead weight of our beam AB as well. So how to calculate design moment for beam AB? Beam self weight, we have 0.225 times 0.45 meters. That's the section of the beam, then times 24, which is the weight of concrete, which gives 2.43 kilonewton per meter. Now, design load from the slab. Remember, from the previous calculation of the slab panel, the design load we got was 9.85 kilonewton per meter squared. So when we multiplied by half of this, the slab span here, we get 15.88 kilonewton per meter. Now the wall load on beam AB, assuming there is no openings and it's 3-meter high, will have 2.47 kilonewton per meter squared times 3, which gives us 7.41 kilonewton per meter. So going further, we add up the self weight of the beam plus the beam wall load. So which is 2.43 plus 7.41, which gives 9.84 kilonewton meter. The reason we are separating this is because the load from the slab has already been factored. So we need to factor the dead load of the beam as well. So factoring the total load, the wall load of the beam and the beam self weight by multiplying by 1.4, we get the design dead load of for the beam of 13.776 kilonewton per meter. So now the total beam design load will now be 13.776 kilonewton per meter plus 15.88 kilonewton per meter, which gives 29.66 kilonewton per meter. So now, as with the slab design moment for beam that is simply supported is WL squared over 8, where W is now the 29.66 kilonewton per meter and L is 6.225 meters. Remember, the span of the beam is 6.225 millimeters. So applying the formula, we get the design moment for beam as 143.67 kilonewton meter. So now we head on to, let's go back to RCC11 spreadsheet and design the beam. So design moment, we change it to 143.67, 143.67, and the span of the beam is 6.225 millimeters. The height of the beam is 450 millimeters. The breadth of the beam is 225. Remember, we are designing it as a rectangular section, and the FCU is 25 and the FY is 410. And okay, so as we enter our parameters, we see that it's designed it for us, provide 4 T20 tension steel bars, giving an area of 1257 millimeters squared. So we see that from what we have seen here, this design seems to have no problems. So the thing is also capable of designing it as a continuous span, support, or cantilever. In the column design, we have many parameters to input as well, but the main parameter we'll be using in this case is the axial load. We won't be calculating for moments because we are designing as simply supported. I want to keep our design simple. And so we move on to the PowerPoint section now, and let's go to the column design section. So now, column design using RCC11. Now we'll be designing the column B. So to design columns using RCC11, you need to have first calculated the load and the moment acting on the column. Now, for design of column B, for this simple design, calculation of moments is ignored. Column B will carry half of the load acting on beam AB and BD. Now, this kind of design where we ignore column movements is good if you are not designing high-rise building, maybe a 1 or 2 story building. This kind of design where you ignore movements is okay. But if you are designing more than a 2 story building, 3, 4, 5 story building, you need to consider uh, the moments acting on the column as well. So uh, when you look at this diagram, you see the load acting on column B. So it gives us an idea of how we can estimate the load carried on column B. Column B will carry half of the load acting on beam AB. This is beam AB and BD. Remember that slab decomposes their load into beams and beams decomposes their load into columns. Moving on, we try to calculate the load carried by B. Load from beam AB carried by column B is equal to 6.225 over 2 times 29.6 kilonewton per meter. Remember from the previous example, we have calculated the design load acting on beam AB. So it makes our design simple by just dividing the span of this beam into 2 and multiplying it by the load acting the load acting on it, and then we get 92.32 kilonewtons. So load of beam BD acting on column B will be 1.4 to bracket. That 1.4 is the factor because it's the dead load factor, and we multiply it by the beam section. That's 0.225 times 0.45 meters times 24, then multiplied by 3.225 divided by 2 plus 2.47 kilonewton per meter squared times 3 times 3.225 over 2. That's the wall load. So this is the self weight of the beam, and this is the wall load, and so we get 22.23 kilonewtons. Of course, although this particular beam may not be receiving any load from the slab, but it could be carrying wall load. So we have assumed for the worst case that it's carrying a wall load. So assuming column B is 3 meters high, now we are now going to add the load of the column itself. So assuming column B is 3 meter high from slab panel to foundation level, self weight of column B is equal to 0.225 times 3 times 24, which is 3.645 kilonewton. So total load acting on column B is 92.32 plus 22.23 plus 3.645, which is equal to 118.2 kilonewton. So we assume load acting at the bottom of the column is 118.2 kilonewton. So now we head over to RCC11 spreadsheet. So we move to the column design, and we change the parameters so that we can see what it is at 118.2 kilonewtons. Let's see. 118.2 kilonewtons. And then let's reduce the moment. We can't, if we put a moment of 0, it might give us an error, but yeah, it's going to give us an error. But let's assume a moment of 0, and then the sectional height and breadth of the beam as 225. Let's reduce the maximum bar size to 16, FCU 25. FY is 410, and let's also use this one as 410. No good, centers too small. centers too small. That means moment must be greater than 1 kilonewton. So let's just add a moment of 10 kilonewton meter. And so let's see if we have a design. Yeah, we have a design. It says us provide for Y16 bars as 2 times 16 top and bottom. So that means 4. It should be reinforced by 4 Y16 bars. So this is how you can carry out designs quickly with RCC11 spreadsheet program. Hope you enjoyed this video. The calculations that I used in determining my design moments and axial load, I have provided PDF copy, a link to the PDF copy in the video's description. Have a nice day.